Hey everyone, I hope you're all doing well. Welcome back to part 3 of our Transformer from Scratch video series. If you're new here, this series aims to provide you with a deep understanding and intuition of why the Transformer architecture is designed the way it is. In each video, we delve into the fundamental mathematics and concepts that underpin this powerful model, allowing you to develop an intuitive grasp of its inner workings. If you haven't already, I highly recommend watching the previous two videos to catch up and ensure you have a solid foundation before we dive into today's content. Building upon what we have covered so far, we will continue exploring the essential elements that make the Transformer architecture so unique and effective. So without any further delay, let's jump into today's video. So let's start off by talking about second order sequence models. And what it is that it's simply predicting the next word based on two words instead of one word, like we talked about in the previous video, which was first order sequence models. So let's say we have these set of possible commands. Check the stove, please. Check the phone battery, please, right? We have these two commands. And let's assume that we use the first command 40% of the time and the second command 60% of the time. We can first represent these commands with a first order sequence model or first order Markov chain, which we talked about in the previous video. So we can quickly review it. So if we were to represent these commands using a first order sequence model, it will look like this, right? So the probability of the next word being the after the word check is 1, right? Because in the possible commands, it's always the after the word check, right? And now, what about the word after the, right? We have stove and we have phone. So we assume that we use the first command, check the stove please, 40% of the time, right? And the second command, 60% of the time. So then we can assume that the probability of the next word being stove after the word the is 0.4 or 40%, and the word phone 0.6 or 60%, right? These are based on our assumptions and our predefined set of possible commands. And then using the same logic, we can see that battery occurs only after the word phone, right? And please happens after stove and battery, right? So this is how we represent these commands with a first order sequence model. Now, what about a second order sequence model, right? Let's see what that will look like. So instead of a single word, we will now have two words, right? So going back, right, the stove, the phone, right? We see that battery has 100% chance of coming after the phone. And we see that please has 100% chance of coming after the stove, right? So this is basically what second order sequence model is. It's predicting the next word based on the previous two words in a sequence, right? They have to be in a sequence for it to be a second order Markov chains, right? Okay. Now we can also represent this using a transition matrix, right? We talked about transition matrix for first order Markov chains already. But basically how it works is that these are the probability of the next words, and see we have two words, check the, right? These are basically based on our sentence and our Markov chain, right? So this is the first order sequence model, just to remind you. And yeah, so the probability of stove coming after check the, right, is 0.4, and phone 0.6. Notice how the row must sum to 1, right? Because it's probability. So if we sum up the entire row, it should add up to 1. And what about the stove, right? After the word the stove, it should be 100% the word please, right? Just like here. And the phone, it should be battery, right? The phone, these two words together, we have battery. So these have to be in sequence for it to be a second order Markov chain, right? We'll see later on what happens if we just skip around, right? If we don't have them being in a sequence. Okay, now I think that's pretty clear. So you might be wondering, why do we even need second order Markov chain if we have first order Markov chain, right? Well, it simply provides us with more confidence than the first order Markov chains, right? It's very hard to predict the next word solely based on the current word, right? If our commands get more complex, it could be anything, right? Yeah, there are hundreds of possible options. So predicting the next word based on the current word and the previous word can probably and theoretically give us more confidence in our prediction, right? I hope that's pretty intuitive. And based on this logic, can't we have third order or even fourth order Markov chains? The answer is yeah, we can, but as sentences and commands grow, it becomes difficult to manage, right? If we have a sentence with 20 words, then this might not even be able to save us, right? So we have to come up with a better solution. This is where we introduce second order sequence model with skips. So for a simple second order sequence model, we only look back at the previous two words, right? Or in other words, the current word and the previous word to predict the next word. Now, however, what if we want to look further back, right? What if the words further back are more important for predicting the next word? So let's say we have these two possible commands. Check the program log and find out whether it ran, please. And the second command, check the battery log and find out whether it ran, please. So in order to predict which word should come after ran, we need to look 8 words back, right? Because these are all the same. Should we use an 8th order Markov chain? No, that brute force solution will not suffice for more complexity. In fact, an 8th order transition matrix will have n to the 8th rows, which is ridiculous for such a small problem, right? So this is where we introduce the clever idea of skips that allow us to capture long-range dependencies. And if you're wondering what n is in this case, it's the vocabulary size, right? The number of distinct words we have in our commands. Okay, so let's talk about the clever idea of skips that allow us to capture long-range dependencies. I want you to keep in mind long-range dependencies because it matters a lot for the transformer architecture, and it's really what inspired the transformer architecture to be the way that it is. So this is where we introduce first the intuition about why we need long-range dependencies, right? And then we will later see in the series how the transformer even solves the problem even better, right? Okay, so for second order sequence models with skips, we simply just have 2 words, right? So these don't have to be together, like right next to each other, like a basic second order sequence model without skips, right? Just a second order Markov chain, right? With skips, we can skip words like battery and ran, right? These 2 words are not adjacent to each other. We are skipping, right? Well, basically how it works is that we're predicting the next word after ran, and we can skip any words to any words before and ran, right? So for example, and ran, and is back here and ran is up here. We're predicting the next word after ran. So if we have the words battery and ran, right, in a single sentence, so it has to be the second command, right? So then the word after ran must be down, right? So the probability will be 1. And what about check and ran, right? There's a 50% chance that it will be down and another 50% chance that it's please, right? Because both sentences have the word check and ran, right? So we can't really tell. Okay. So now these word combinations can be considered features, right? Features that help us decide what the next word will be. This is pretty much out of the range for Markov chains because these words are not adjacent to each other anymore. They're skips. They can be skipped around, right? Which violates the Markov property. Now, what if we treat these probabilities as weights, right? Or votes? We can simply sum them up for each word and determine the word with the highest weight or vote total to predict the next word accurately, right? So if we want to see what is the total weight for the word down, right? So based on all these skip word combinations with ran, right? It ran, whether ran, outran, find ran, right? We can have all of these word combinations and we simply sum up. So for the word down, we will add 0.5 to 1 to 0.5 to 0.5. And for the word please, we'll add 0.5 to 0 to 0.5 to 0.5 and so on, right? We sum them up for each word here. And whichever word has the greatest amount of total votes or weights is the word that's most likely to happen or occur next, right? I hope that's pretty intuitive, right? So we're skipping around to associate the word ran with more important words, right? That have greater weights. For example, battery and ran, right? Battery has a lot of weights because it determines that the next word has to be down with 1% chance, right? 0% for please, right? So I hope that's clear. And this is more effective than a simple second order sequence model because it allows us to focus on the important word combinations, right? And one thing to note that this is like no longer a Markov chain since we allow for skips, right? We skip around, which doesn't obey the Markov property. And as we'll see in future videos, that the idea of long-range dependencies is very important for the transformer architecture. And this idea of features is also very important. Okay, so just a quick recap. We talked about what a second order sequence model is. It's basically taking the previous two words to predict the current word, or in other words, take the current word and the previous word to predict the next word, right? So the probability of the word battery coming after the word the phone is 1, right? And we talked about how we can represent this using a transition matrix, like in this case here, right? And we talked about how each row must sum to 1, right? Because it's probabilities. And we talked about the importance of second order sequence model, why it's better than a first order sequence model. And then we talked about intuition for second order sequence model with skips, right? Why the idea of skips is very crucial. And yeah, we talked about second order sequence model with skips. and the idea of long-range dependencies and features and votes/weights to determine the next word. And I hope you guys found this video helpful. I think that's it for this video. So if you have any questions, please feel free to leave them down in the comments below. I will try to answer them as soon as possible. Please ask any questions that you want, and I will try to clarify them. So yeah, also if you have any suggestions for my future videos, please leave them down in the comments below so I can improve my contents. And if you found this video helpful, please subscribe and like this video, and stay tuned for further videos in this video series. Yeah, thank you guys for watching, and I hope you have a good day. See you next time.